Hello, welcome to this lecture of Biomathematics. In this lecture, we will discuss one application of a few things that we have learned so far. So, something we learned in probability and something we learned in transforms. We learned about Fourier transforms and Z transforms. So, how do we apply this transform as well as some ideas from probability together to understand some of the biological phenomena. So, that will be the aim of this lecture. In the probability theory, we said the probability of finding something, we also learned something about differential equations. So, all of the many things that we learned so far will come together and we apply that to a problem in simple problems in biology, and then we will see how do we use these ideas basically to solve this problem. So, let us take one of the examples that we learned, we came through before. So, let us take this example. So, what we will, the title of this lecture is master equation, polymerization dynamics, molecular motor motion. So, we will write an equation for understanding either polymerization or molecular motor motion, and we will try to solve this. And while doing this, we will use ideas from probability and differential equations and also from transforms. Some of the transforms that we learned will be used here. So, this is also an example of how this kind of transforms that we discussed were some f of x is converted to some other f of k or g of k can be used to solve differential equations. Okay, so, let us take this example of polymerization and depolymerization dynamics. So, let us say with some rate alpha. So, you have a filament here, and with some rate alpha you can polymerize, and with some other rate beta it can depolymerize. So, this is the simplest case one can think of, polymerization and depolymerization. And let us define something called P and T, where P and T is the probability to have n monomers on the filament. So, you can have 1, 2, 3, 4 here. So, this 4 can increase to 5 or it can decrease to 3. So, the P and T is the probability to have 4 monomers at any time t. What is this probability? So, that is what is defined by this P and T. So, how do we define this probability? So, one can think of basically, so let us say you do an experiment where you think the length of the polymer as a function of time. So, you start with let us say some seed, then for some time, then suddenly it increases, remains same, it can increase, decrease, it can something like this can happen, it can polymerize like this and go. So, essentially length versus time can increase depending on if the polymerization rate is more, but it can just keep changing with time. So, now you do many experiments. So, you can think of one doing many experiments. So, let us say one experiment have length as a function of time like this, another experiment has length as a function of time like this, another experiment has length as a function of time like this. All of them on an average same slope, same increase, but you can imagine that the length as a function of time can have different curves. So, now you can ask the question, after a time t, what is the probability that you will find at a particular time t, what is the probability that you will find the length as exactly let us say this. So, this particular length, the probability here is very small, because all of this have only this So, the probability here, the most of the time the length is somewhere here. So, the probability to find this length, only one configuration here, you can see that having this particular length. You can ask the question, what is the length which is this? The probability to find this length is in this particular case 0, because there is none of the configurations have this particular length and this particular time. So, you can always imagine writing probability that you will find a length L at a particular time t. So, this is same as P of n t. In other words, what is the probability you have n monomers at a particular time t. So, L is n times d, where d is the size of the monomer. So, if d is the size of the monomer, L is n d, and so you can, instead of P of L t, you can also think of P of n t, where probability to have n monomers at time t. So, you can see that you can think of getting different values. Similarly, same idea can be extended to molecular motors. So, let us say you have a molecular motor walking on microtubule. Let us say this is typically, as you know, like motors like kinesin, dynein, they walk on microtubules. So, let us say this is microtubules are like a track. So, let us say you have a molecular motor here, a particular motor here. This can go here or go here. So, let us say you start from somewhere here at t equal to 0. So, you start from but here at t equal to 0. Then you can ask the question, what is the probability that it moved n distance n, it moved n sites, at a particular time t. What is the probability that it moved a distance of n subunits at a particular time t. So, this is also in the same way as polymerization, depolymerization. At any point, it can go to the next one with some rate alpha, or it can go to the previous monomer. It can move, it is moving along the monomer, basically the molecular motor. So, even for molecular motor, we can define something called P and T, which is the probability that it would have moved a distance of n monomers in a time t. So, both for polymerization and depolymerization or motion of a molecular motor, one can define P of n t. It's the same way as we said, if you plot how far the number of monomers it moved in a time as a function of time, if you do one of this curve, you might get something like this. Another one experiment, if you do one experiment, let us say you fix a particular concentration of ATP, for a particular concentration of everything, and then look at one molecular motor or one polymer or one filament, and then you look at how does the length changes with time, or how does the number of the distance moved changes with time. It might get, in one experiment you might get this, in another experiment you might get something like this, in a different experiment you might get something like this, in a completely different experiment you might get something like this, in another experiment you might get like this, even though on an average you get this, but each time you might get a different path. So, what does that mean? That means at any particular n and at a particular time, the probability differs. So, here only one configuration has this particular n at this particular time. On the other hand, here there are many configurations at this particular time and at this particular length, there are many configurations. So, we can ask the question, how many times it gets this particular length at this particular time. So, from that you can calculate probability P of n comma t. So, in principle one can think of a P of n comma t, which is the probability to have n, in the case of polymer is n monomers at a time t, or in the case of molecular motor, probability such that the molecular motor has moved a distance of n subunits at time t. This is, or you can, the probability that you find molecular, you can also define it, probability that you find molecular motors in the nth location. So, you can think of this 1, 2, 3, 4, 5, like you can define, and again this might be your n. So, what is the probability that you find molecular motor here at a particular time t? So, that is p n t. So, we will mostly, so just now how does the p n t changes? How does the p n t changes? So, we can write something called d p n t by dt, the change in probability. So, the probability can change. How does, what is this dpn? How does the probability change with time? So, this equation for change in probability dp by dt, this is called master equation. So, if you write the equation for probability, typically it is called master equation. So, this is what we will discuss, master equation. Master equations are typically equations for probabilities. So, we will write how does this probability changes with time. So, now let us think of the first case for the polymer. If you look at here, so let us say you had 4 monomers, 1, 2, 3, 4. From this, it can go to 5 monomers, 1, 2, 3, 4, 5 by adding a monomer. So, this is with the rate alpha, it can change, it can go away, it can go to this. It can go to 3 monomers, 1, 2, 3 with beta, because what you are doing is removing a monomer. So, this is you are adding a monomer. If you remove a monomer with a rate beta, you can go to this kind of a filament. So, by adding and removing, this p and t will change. So, if you had 4 of them at a particular time t, this will change through alpha. So, by doing an alpha, this probability changes. With beta also the probability changes. But in both the cases, what happens is that it is the probability decreases, because it is going away from this 4. It is going to 5 here, it is going, so the p4t decreases. So, I have to put a minus sign here. So, in this case, in both the cases we discussed here, the p4, the probability to find 4 decreases, because here the probability it goes from 4 to 3, here it goes from 4 to 5. So, in both these examples we discuss here, this p4, the probability to p4 decreases, because if it polymerizes, the p4 decreases. If it depolymerizes, so the p4 decreases. So, let us say, in other words, you can think of this particular way. You have a test tube which has like many filaments. So, let us say there are like many filaments having length. So, you can think of like this is 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So, these are 3 filaments with 4 monomers. Now, let us say there are some with 2, some with 3, some with 5, 1, 2, 3, 4, 5. So, this is 5, this is 2. So, there are all kinds of all kinds of filaments having different length. So, there is, let us think of this. So, there is one total number of filaments is 1, 2, 3, 4, 5, 6. So, there are total 6 filaments, out of that 3 is having 4. 3 of them have 4 monomers. So, the P of 4 is 3 by 6, which is basically half. So, this is 0.5. The probability in this particular example, the probability to have 4 monomers is actually half of them have 4 monomers. Now, let us say some depolymerization happens in any of them. So, then let us say this depolymerizes, then what happens? This becomes 3. If this becomes 3, so there is only 2 out of 6, you will have 3, 4, the number of filaments having 4 monomers will decrease. So, then the probability becomes P4 becomes less. So, essentially dP4 by dt can decrease if there is a depolymerization. So, which is beta, and you have to have 4 of them. If it is proportional to P4, because if only there is P4 filament with 4, you can go away from it. You can also go away. You can also go away by alpha. That means, if you polymerize any of this, number of filaments with 4 will decrease, because this will suddenly become 5. If this suddenly becomes 5, only 2 of them have 4 monomers. So, dP4 by dt will decrease. The essentially P4 will decrease. So, the master equation that we think of, dPn by dt will decrease with alpha, will decrease with beta, plus there is a few more things going to happen. So, what is this? Now, let us say imagine that you have a case. So, this has 4 monomers, this has 4 monomers, this has 3 monomers, this has 5 monomers. So, if there are if there is a polymerization happens on a 3 monomer filament, this will become a 4 monomer filament. So, P4 can increase if there is a polymerization on a filament having length 3. So, dP4 can increase, it can increase, plus if there is a polymerization, that is alpha, on a filament with 3 monomers. Similarly, let us say there are 5 monomer filament. If this depolymerizes, this will become a filament with 4 monomers. If there is a depolymerization happens on a filament having 5 monomers, the 5 will become 4. So, this will become a filament with 4 monomers. So, if there is a depolymerization with the rate beta happens on a filament with 5 monomers, that also can increase P4. Then, if this happens also, the probability to have 4 monomers will increase. So, here the n can decrease with alpha and beta, and it can increase given that a 3 comes to 4 or a 5 comes to 4. So, this is n. So, this is 3 is n minus 1 and this is n plus 1. So, whatever here is alpha into P n minus 1 plus beta into P n plus 1. So, these are the only things can happen. It can happen polymerization from n minus 1. If there is, so let me write this little more neatly. So, if we write this little more in a better way, dPn by dt is equal to alpha into P n minus 1 plus beta into p n plus 1 minus alpha into p n minus beta into p n. So, what does this mean? So, this is the master equation for how does the p n changes with time. Probability to have n monomers, sometime I will write as p n, sometime I also write p n. So, both are equal. I might use both the notations, but here I use this notation for simplicity. So, what does this mean? This means that if you have a monomer, if there are a lot of filaments with n minus 1 monomers, they can polymerize with a rate alpha and go to Pn. If there are a lot of monomers with n plus 1 filaments, there is a lot of filaments with n plus 1 monomers, they can depolymerize with the rate beta and then go to dPn by Pn. If there is many filaments with n, they can polymerize and go to n plus 1. That means it can go away from Pn. So, the Pn will decrease. If there is a lot of filaments with n, some fraction of filaments with n, it can also depolymerize and go away from Pn. So, the Pn will decrease. So, this is the master equation for polymerization, depolymerization of filaments. Same thing can be said of molecular motors. If you find a molecular motor at a particular position n, so if you, so this is n, this is n plus 1, this is n minus 1. So, dPn by dt, if there is a molecular motor already here, that is, it's already the probability, it can go away and then the Pn will decrease. So, if there are, like, imagine many filaments. So, imagine same thing, like let us say you have like many filaments. In all these filaments at a particular n, so n let it be here. If there is a molecular motor here, this is the position n on each of this filament. N could be like let us say 10th monomer. So, if at a particular position 10 there is a monomer, there is a molecular motor, this molecular motor can go away to n minus 1 or n plus 1. So, the rate of going away could be, so if it goes away, then the Pn decreases. If it moves here, the Pn decreases, the probability to find a molecular motor at a position n decreases. If a molecular motor goes to this side also, the same thing happens. So, this is same as minus alpha Pn minus beta Pn. Similarly, if you have a molecular motor here, it can come here. If there is a molecular motor, it can come here. So, this n can increase by a molecular motor moving from n minus 1 to n plus 1 or n plus 1 to n. So, you can write dPn by dt is the same equation what we describe here applies exactly the same way to the molecular motor also. Okay. So, this is the master equation. So, essentially, so in the case of polymerization, depolymerization, the master equation, as you can see here, is dPn by dt is alpha into Pn minus 1 plus beta into n plus 1 Pn plus 1 minus alpha plus beta Pn. So, this is the master equation. So, now we have this master equation. Now, the question is, how do we solve it? How do we solve this equation? So, it is not that. So, here is where we will make use of some of these transforms we learned. So, we defined Fourier transform in this particular manner, where we said if you have an f of x, if you have a function f of x, you can multiply with e power I k x and integrate over x, and you get some other function. Let me call this f tilde of k. So, sometimes I call g of k f tilde. What does it only means? The some function of k. Tilde only represents some different function. F is different from f tilde. So, some different function of k you might get. We also said a z transformation. You can also think of this writing in a different way. I can also write this as f of x e power minus kx dx. This is also, you can call this f tilde of k, some other definition of transformation. The inverse transformation will be defined in a particular different ways for this. There will be inverse transformation will be different for this and this, but you can define such transformation. So, today we will use one such transformation similar to this discrete version of this. So, what we will say is that, so we have p n of t. So, we say that p of n comma t e power minus k n sum over n over all n, like let us say minus infinity to plus infinity, whatever be the n for the whole range. If you do that, let us define this as p tilde of k comma t. So, this is the definition. If we can define such a function, we can make use of this and solve the differential equation in an easy way. So, we want to define a new function which is p tilde of k of t. So, if we know p of n of t, we can always calculate p tilde of k of t by multiplying with e power minus k n and summing over n. So, this is if n for various values of n, you can calculate probability to have 1 at time t into e power minus k, probability to have 2 at time t into e power minus k into 2 plus so on and so forth. So, you can expand this and define some particular p tilde of k which is in this particular manner, right. You can think of this like, so let us say probability to have 0 at time t into e power minus k into 0 plus probability you have 1 at time t into e power minus k into 1 plus probability to have 2 monomers at a time t into e power minus k into 2 plus probability to have 3 monomers at time t into e power minus 3 into k plus dot dot dot. You can do this sum and calculate this p tilde. So, if we know this p's, we can always calculate this p tilde by this particular definition. So, this is the definition of p tilde of k. So, that is what I have written here. P tilde of k is defined as sum over n p n t e power minus k n. Now, what is our master equation? Our master equation is that d by dt of p n comma t is equal to alpha into p n minus 1 comma t plus beta into p n plus 1 comma t minus alpha into p n comma t minus beta into p n comma t. So, this is the master equation that we wrote a minute ago. We can multiply throughout by e power minus. So, you can do a transformation for this whole thing. So, what can we do? We can multiply everywhere by e power minus k n and sum over n. So, you can do sum over n e power minus k n, sum over n e power minus k n, sum over n e power minus k n, sum over n e power minus k n. So, I do multiply everywhere with e power minus k n and sum over n, both sides throughout the equation. So, then what do we get? So, what is this? Sum over n p n t e power minus k n. So, as we defined here, so if you look at the definition here, sum over n p n e power minus k n is p tilde of k. So, sum over n p n e power minus k n here becomes p tilde of, so this I can write as d by dt of this blue part alone, this part alone becomes p tilde of k comma t. Even this becomes p tilde of k comma t, this also becomes p tilde of k comma t. So, these three terms, so this is p tilde of k comma t, this is p tilde of k comma t, this is also p tilde of k comma t. So, let us rewrite this a bit. So, here I write d, if you look at here I will write, so if let us carefully look at here. So, let us look at this equation little more carefully here. So, this term I call this, so d by dt of, this is p tilde of k comma t. So, p tilde of k comma t. Now, what is this term? Let us look at these two terms here. So, let us look at this term and this term. So, minus alpha into p tilde of k comma t. So, that is what this term will give you, and this will give you minus beta into p tilde of k comma t. So, there is p tilde, this and this are same. So, I can take it out in common and I can write minus of alpha plus beta. So, just look it carefully, you can write minus of alpha plus beta into p tilde of k comma t. So, this is these two terms. Now, I have to do this two term, but those two term I will, let me write this particular way. So, this is plus alpha into sum over n p n e power minus, sorry, p n minus 1 e power k n. Here it is plus beta sum over n p n plus 1 e power minus k n. So, now this is, if this were n, sum over n p n e power minus k n, I could have defined it as p tilde of k, but this is not n, this is n minus 1. So, I can do a small trick here. So, the trick is, let me define m is equal to n minus 1. So, let me define n minus 1 as m. So, let me define, if we define, so let us do a trick here, this is a small trick which we can use. So, let us say if we define m is equal to n minus 1, what is n? N is equal to m plus 1. So, instead of, so wherever n, I can write m plus 1, wherever n minus 1, I can write m. So, this is some, I call it n minus 1 as another, n minus 1 is a number anyway. So, I call this n minus 1 as m, and so what happens to this term? So, let us look at this term only. If we look at this term carefully, what do we get is that, if we look at this term carefully, what do we get is that this term gives to, what does it give? Alpha sum over n. So, let us say n is, now this has to become m. If n was infinity, it will become infinity plus 1 or infinity minus 1. So, infinity plus 1 or minus 1 does not really mean anything, infinity itself. So, this n and m is just only different by 1, and the limits does not change because they are infinities. So, then you have p of n minus 1, n minus 1 is m. So, let us write p of m, e power minus k n, e power minus k n is m plus 1. So, let me write m plus 1. So, this term becomes alpha into sum over m p m e power minus k into m plus 1. So, this can be written as alpha into sum over m p m e power minus k m, p m e power minus k m into e power minus k. So, you can see this e power minus k m plus 1. So, this can be written as e power minus k. So, this can be written as this, and this particular part, if you look at just this thing, this we can call again p tilde of k. So, this is our p tilde of k. So, what you get there is alpha times p tilde of k into e power minus k. So, that is what this term will end up. This term will end up as alpha into p tilde of k into e power minus k. If you do this trick of calling n minus 1 as m, since the limit does not change, this infinity and infinity plus 1 and infinity minus 1 does not change anything, this whole thing becomes p tilde of k e power minus k. So, this whole thing becomes p tilde of k e power minus k. So, similarly, I can also do a trick on this. So, the next term, let us carefully look at it. So, the next term is b sum over, if you look at here, the term is beta sum over n p n plus 1 e power minus k n. So, let me write that term here. The term is beta sum over n p n plus 1 e power minus k n. So, here I will use the trick, I will call n plus 1 equal to some m. I could call m or q or p or whatever, another integer. Then wherever I substitute n plus 1, I could put n, and wherever, so that means n is equal to m minus 1. So, this whole thing becomes beta times sum over m, p n plus 1 becomes p m, e power minus k n becomes m minus 1. So, this is m minus 1. So, what is this? Beta times sum over m p m e power minus k m into e power plus k. So, this whole thing becomes p tilde of k again, and this is e power k. So, this becomes p tilde of k e power k. Previously, we had there p tilde of k e power minus k. So, this term becomes p tilde of k e power k. So, if you rewrite if you consider whatever we discussed so far and do it properly, to take carefully and write everything, what you get is that d p tilde by dt is equal to minus alpha plus beta into p tilde of k. So, this is all this at a particular time t plus alpha into p tilde of k e power minus k plus beta into p tilde of k e power k. So, this is what you will get. In other words, I can combine this alpha term and this alpha term and write it as alpha, sorry, I can write p tilde of k and there is e power k here and there is minus alpha e power k, then there is minus alpha. So, I can write p tilde of k into e power minus k minus 1 into alpha plus e power k minus 1 into beta. So, this is the equation you will essentially get. So, if you look this carefully, if you carefully look at it, what you get is that if you write this carefully, what you get is that d p tilde by dt is alpha p tilde e power minus k plus beta p tilde e power k minus alpha plus beta p tilde of k. So, then as we just rightly wrote here, this can be written in this particular manner. So, if you look at it, what you essentially get is that d p tilde by dt is some function of k times p tilde. So, let me call this, write this equation in a different way. So, d p tilde by dt is some function. So, let me call this some mu of k, some function of k into p tilde. So, if you have such an equation, you can easily find the solution. You know that if you have dy by dt is equal to some other mu times y, you know that this is a solution which is y is equal to e power, some y is equal to y 0 e power mu t with some constant a here. So, you can know that immediately this has a solution like this, which we discussed some time ago in differential equations, because you can write this dy, take this mu y downstairs, integrate both sides, you will find this is an exponential solution. So, just similar to that here, what you have is here that an exponential solution. P tilde of k t has an exponential solution e power this. So, we could immediately solve this. It becomes a very simple equation. So, previously we had a complicated equation here in terms of alphas and betas, that becomes a simple equation like this, and it could easily find a solution. So, you could find the solution, which is p tilde of k of t is a e power a p tilde of k of t is equal to a e power alpha into e power minus k minus 1 plus beta into e power minus k minus 1 times t. There is a minus typing error, this has to be plus k. So, here it is e power plus k, sorry, here it is e power plus k and here it is e power minus k. So, this is what the solution you will get. Now, what is a? How do we find out a? We can find out this normalization condition. The normalization condition is that if you sum over all probabilities, you should get 1. That means there is no, again another small typing error, there is no tilde here, it is sum over n, p n has to be 1. So, what we have is the sum over n, p n at a particular time has to be 1, because at any particular time there will be probability to have 0 filament plus 1 filament plus 2 filament, probability to have filament of 0 length plus 1 length plus 2 length, 3 length. So, if the probability to have n monomers for any, at least the sum of all probabilities has to be 1. So, by if you use this, our definition of p tilde of k of t is sum over n p of n comma t e power minus k n. Now, if you take k equal to 0, that is p tilde of 0 comma t, what do you get? You get sum over n p of n comma t e power minus k 0. So, this is 1. So, this is just sum over n p and t, and we know that sum over n p and t is 1. So, this has to be 1. So, p tilde of 0 comma t has to be 1, and we have a solution for p tilde of k comma t here. So, now if you put k is 0, this whole thing has to be 1. So, if you put k 0, so this is 1 minus 1 0, here also 1 minus 1 0. So, this whole thing is 0 on the e power 0 you get. So, you get p tilde of k 0 comma t as a. So, if you do this, if you do this calculation and p tilde of 0 comma t, you will find that this is a and this has to be 1. So, this implies that the normalization constant a is actually 1. So, that is what we find, that the normalization constant a here is actually 1. So, we find this. So, we could easily solve it and we could find out this constant. Now, if you really want to get p of n comma t, we have to do an inverse transformation of this. We can do that in principle and get it If it is an easy function, you can easily do it. If it is a difficult function, one can do it numerically, but either way, one can get a easy solution for this equation in the k form, and you can always transform back this to the n form. So that is one idea of doing this transformation. But there is another interesting thing which you can see is that if we have this definition of, so how did we, let us think of this definition what we did. So what we did was p tilde of k comma t was defined as sum over n p n comma t e power minus k n. Now, if I take a derivative on both sides with k, so let us say I do a del by del k of p tilde of k comma t. This is nothing but del by del k of sum over n. So, sum over n I can take outside. So, let me write here only sum over n p n comma t e power minus k n. So, I can take this outside. So, this can be written as sum over n, and if you find the derivative of e power minus k n, there is a minus k will come out. So, there is a minus. So, there is a k, sorry, n will come out, minus n. So, this is n p n t e power minus k n. So, one derivative with respect to k will give you this. Now, if you put a minus sign here, you can put a minus sign here, this will become plus. So, what you find is that minus del by del k of p tilde of k comma t is sum over n n p n t e power minus k n. So, let me write this. This has a significance. So, what did we find? We find that minus del by del k of p tilde of k comma t is nothing but sum over n n p n t e power minus k n, n p of n comma t e power minus k n. Now, if I put k equal to 0 in this, so I calculate this at k equal to 0. So, that is, if I calculate del by del k of p tilde of k comma t and then put k equal to 0, apply k equal to 0, evaluate this at k equal to 0. So, then what you get is sum over n n p of n comma t, and when k is 0, this is 1. So, this is what you get. So, minus del by del k of, if you find the one derivative of this transformed version of the probability, if you find a derivative with respect to k of the transformed version of the probability and you calculate this at k equal to 0, put k equal to 0 after doing this, what you get is sum over n p n t. So, we have learned that sum over x p x t, this is nothing but n average. We learned that in the time of when we learn probability, we learn that sum over n p n is n average, sum over x p x is x average, or integral x p x dx is x average. So, this is the definition of average n. So, this is nothing but the average number of monomers can be easily calculated by finding the derivative of the newly found, the transformed probability p tilde of k with respect to del k. So, this we already found, and by just doing one derivative we get the average number of monomers on the filament. Now, let us say this average number of the monomers can be depend on time. Sometime it keep the average can be small, later after some time the average can be high. So, you can also find a derivative of with respect to time derivative. So, you can say d n average by dt is how the average number changes. So, we can call this the velocity of growth, and this can be found essentially shown as del by del k of minus del by del k of p tilde of k comma t. So, this is you can in this way we can define the velocity. So, if we define the velocity in this particular way, so as we just discussed now, we can write del d by dt of del p tilde by del k at k equals 0 as dn by dt, and this will give you velocity. So, this is just we discussed. If you find the one derivative with respect to k, what you essentially get is n p n t power minus k n, and if you calculate this at k equals 0, there is again this has to be evaluated at k equals 0, it will give you n average, and then this is what the correct statement is. My d by dt of minus del p tilde by del k at k equals 0 is average, n average. So, and we know this p tilde, and then v can be calculated as dn by dt and d by dt of del p tilde by del k at k equals 0. And if we do that, we know that dp tilde by dt already from our equations, and if we find del k by del t and evaluate at k equals 0, we will find that v is alpha minus beta. So, we can also calculate the velocity of growth, or the velocity of growth is basically polymerization rate minus depolymerization rate, as you can see here. So, v, you will end up finding that v is alpha minus beta. This is the rate of polymerization minus the rate of depolymerization. Similar on the case of molecular motor, this is the rate of moving forward minus the rate of moving backward. So, this is the velocity of the molecular motor, which is the rate of moving forward minus the rate of moving backward. So, essentially what we quickly showed is that if you use the ideas that we learned for molecular for probabilities and for transforms, we can apply that for simple problems like that the velocity of molecular motion of the molecular motors, or the polymerization growth velocity, the average length of the filament, the average distance the molecular motors moved, etc., can be easily calculated. So, we will learn more applications in the coming lectures. In this lecture, with this we will stop today's lecture, and we will discuss more in the coming lectures. Bye.